The next question of CODECHEF starters 118 is it uniquely decodable? So basically in this question there is a password which comprises of only digits 1, 2 and 3. So now this password is encoded in the form of a string which consists of A's and B's. So digit 1 is encoded as AB, digit 2 is encoded as ABA, and digit 3 is encoded as A. So now a string is called uniquely decodable if it consists of only A and B, as the encodable strings have only AB characters. So for sure it should consist of A and B, and there should only be one possible way to decode the string. So for example, if we consider AB, A, B, A, this is not uniquely decodable because I can decode these two as 2 and this as these two as 1 and this as 2, right? And there is also one more way to decode, that is I can make these two as 2, this as 3, uh, this as 1 and this as 3, right? So here there are two ways. Because there are two ways, this is not uniquely decodable. Now if we consider a string AB, AB, then here we can observe that there is only one way, that is 2 and 2. It is only decodable in one way, that is these two can be made as digit 2 and these two things can be made as digit 3, right? So now a string S is said to be decodable if it consists of only characters A and B, and the string is uniquely decodable, uniquely decoded. There is only one way to decode it, considering this mapping. So considering 1 is encoded as AB, 2 is encoded as ABC, and 3 is encoded as A. That means while decoding, AB should be decoded as 1, ABA should be decoded as 2, A should be decoded as 3. So from this, this string should have only one way in which it is decoded from the given mapping. Then it is uniquely decodable. Now in the question, we are given a string S. Yes. So now we should find out how many subsequences of string S are there, which are uniquely decodable. Decodable. So this number of subsequences of string S which are uniquely decodable can be large also. So we are given with 10 power 7, 10 power 9 plus 7. So we should print the result modulo 10 power 9 plus 7. So a subsequence of any string is nothing but, let's consider a string AB. Then subsequence of this string is some set of indices, is just some set of characters that we pick from the string in order. That is, if we consider for this as first, second, third, and fourth, fifth characters, third, fourth, and fifth character, then AB, this is a subsequence, A is a subsequence, one more A. That is only this is a subsequence. B is a subsequence because we pick this one, and this. So subsequence, the characters that we pick, they should be in order only in the string. Now, if we see A is not a subsequence. A is not a subsequence because this don't follow the order. So all such strings are called subsequences. So among all these subsequences, we should find out the number of subsequences which are uniquely decodable. So now if we look at the constraints of this problem. So here we are given with test cases. So test cases can be in the range 1 to 2 into 10 power 5. And length of the string can be in the range 1 to 2 into 10 power 5 in the worst case. And it is guaranteed that summation of length of the string will be in the range sum of length of string s over all test cases will be in the range 1 to 2 into 10 power 5. So let's see how we can solve this problem. So firstly, to solve this problem, the prerequisite is dynamic programming. So let's make some observations first. So for a string to be uniquely decodable, firstly, in the string, we shouldn't have two b's, right? Because if two consecutive b's exist, then then like there is no way to encode. If we look at the mapping, no character is encoded which is starting with b, or no character is encoded which has two b's in it, right? So we can just see that no character is encoded which starts at b. So that is the reason we can't have two consecutive b's. So from the mapping we can observe that. And secondly, if we observe, we shouldn't have a substring which has a b a in it. Why? Because if we have a b a in it, then this part can always be encoded in two ways. ABA can be encoded in two ways. That is, we can either encode it as 2, or we can encode it as 1 and a 3. So this will violate the uniquely decodable criteria. And in the third scenario, our string shouldn't end with ABA, because if string ends with ABA, then the same condition holds. That is, we can decode this in two ways. We can decode this in two ways. That is with digit 2 or with 1 and a 3, digit 1 and a 3. So these are the three things that shouldn't be present in our uniquely decodable string. If the string need to be uniquely decodable, these are the three things that shouldn't be present. But we can have something like AB, AB. That is because though we have ABA, in case if I decode this with 2, then for sure I won't be able to decode the next thing. Why? Because there is no character encoded which starts with B. So we can have a string which is AB. This is not a restriction. So in this case, it is always uniquely decodable. That is, we can decode it as 1 and so only conditions which violates uniquely decodable criteria is having two consecutive B's, or ABAA or ABA. So now, in case if we encounter a B, then we can see that the next character should only be A. Similarly, in case if we encounter a ABA, we can see that the next character should only be B. And yeah, these are the two criteria. And we should ensure that string won't end with AB. So now, because these are the required criteria, we can use dynamic programming for this to handle, like, we can put track of what characters were taken previously, and depending on that we can make choice whether to put a or a B currently in the current position. So let's define our DP states. So we can define our DP as follows: DP of n of 3, and we can even perform memory optimization on this. Firstly, let's define the states and transitions, then let's see how we can optimize the memory. So DP of I of 0 defines using first I characters of S. What is the Using the first I characters of S, how many uniquely decodable subsequences that we can have, which end with A, which end with last character as A, as A, and last second character not equal to B. And last second character can even be empty. So DP of I of 0 tells us, using first I characters of S, how many uniquely decodable subsequences that we can have, which subsequences of S uh, okay, we can say how many decodable subsequences of S, considering first I characters of S only, that we can have, which end with last character as A and last second character not equal to B. So last second character can be empty also. It can be empty or A. So how many such subsequences do we have? How many such subsequences did we find till now is what DP of I of 0 stores. Now DP of I of 1 stores using first I characters of S, how many uniquely decodable subsequences that we have. that can have, which end with last character as B and last second character as A. As A. So how many such subsequences do we have? So basically dp of I of 1 tells us, using first I characters of S, how many uniquely decodable subsequences that we have, considering only those first I characters, which end with last character as B and last second character as A. Similarly, dp of I of 2 tells us, using first I characters of S, how many uniquely decodable subsequences that we can have, which end with character as which end with last character as A and last second character as B. As B. So how many such subsequences do we have? So dp of I of 2 tells us, using first I characters of S, how many uniquely decodable subsequences that we can have, which end with last character as A and last second character as B. So that means ultimately, uh, in this case, we are putting track of all the subsequences which have some characters and end with BA, right? That means for sure here we should have a A. So we are basically tracking how many subsequences are there which are ending with ABA. So if they end with ABA, they can never be decodable, right? So the definition here is, using first I characters of S, how many uniquely decodable subsequences that we can have, which end with last character as A and last second character as B, excluding the last character. Right? So basically, in this case, we got some string. Now, if we consider the whole string, then it might not be uniquely decodable. But here it is, we are counting all such strings which end with A as the last character and last second character as B. And if we consider the string till the last second character, then it will be uniquely decodable. Whereas the including the last character, it won't be uniquely decodable. Such strings, all such strings. So these are the three uh, states that we have. So first state is, using first I characters of S, how many uniquely decodable subsequences that we can make, which end with last character as A and last second character not equal to B. But that can even be empty. Last second character can even be empty in the first case. And the next state is, using first I characters of S, how many uniquely decodable subsequences that we can have, which end with last character as B and last second character as A. And dp of I of 2 tells us, using first I characters of S, how many uniquely decodable subsequences that we can have, which end with last character as A and last second character as B, excluding the last character. So excluding the last character, the string will be uniquely decodable. That's what this statement means. Now let's look at the transitions. Transitions for these states. So here, as only our uniquely decodable string should have A and B characters, we can make transitions when the character is either A or B. So let's say ith character is A. So now let's see how we can make the transitions in this case. So initially, yeah, before this, firstly, dp of I of 0 will be equal to dp of I minus 1 of 0. That is because if we could make number of if we could make certain number of uniquely decodable strings which end at A and does not end at B, does not which end at the which has ending character as A and the second last character not B. Basically, uh, considering first I minus 1 characters of S, if the last ending character is A and last second ending character is not B, all such substrings that we could make using I minus 1 string is dp of I minus 1 of 0, right? So using I minus 1 characters of the string, that is this. Now the same number of substrings we can make using I characters of the string also, right? So similarly, dp of I of 1 tells us, firstly, if we could make now all the substrings which which are uniquely decodable and end at B and have last second character as A using I minus 1 characters of string S, then we can make the same number of strings using I characters also. So that is why it is dp of I minus 1 of 1. Similarly holds for the next two. If we could make this count of substrings depending on the state definition of 2, then we could make the same number of substrings using I characters of S also. So initially, using I characters, making all substrings which end at A and does not have second ending character as B is nothing but number of substrings that we could make using I minus 1 characters of the same state. Similarly, holds for dp of I of 1 is equal to dp of I minus 1 of 1 and dp of I of 2 is equal to dp of I minus 1 of 2. So all the subsequences that we could make using I minus 1 characters could be made with I characters also. So that's why we could just do this. Now, including the ith character, what all new subsequences that we could generate is the question. So for that, firstly, either the ith character should be a character A or character B, right? Because this is if we don't include the current character. So we can just consider these transitions as if we don't include the current character or in the previous way. So the best way to define these transitions would be we are making decision on including the current character or not including the current character in the subsequence. So here these transitions correspond to if we don't include the current character, then it is just number of subsequences of that state that we made using I minus 1 characters. So all these are if we don't include the current character. SOFM. And now we are calculating if we include the current character. So if we include the current character, then firstly the character should either be A or B, because if there is some other character, then we can't include that in our subsequence as it is not uniquely decodable. So if it is a A, then dp of I of 0, that is the last character is a and last second character is not a last second character is not a b. So for this we can just include all the subsequences that include a, like we can just add up all the subsequences whose last character is a and last second character is not a b. So we can just add up all these values, and we even do a plus one. That is because we can start a new a also now, right? So this represents we are starting a new subsequence. We are starting a new subsequence. And one more transition could be dp of I of 2, that is ending with a and last second character is a b, right? So we could reach this state from dp of I minus 1 of 1. This means all subsequences using I minus 1 characters which end with a b as the last character and the last second character is a a. So that just means this will include all the substrings that are uniquely determined, excluding the last character, where the last character is a and last second character is a b. Right? So this is the transition when we have a. Else, if we have a b, and if we are making decision to pick the b, then only state that gets affected is having last character as b and last second character as a. So dp of I of 1 will be equal to, so we can add a b considering last character as a and last second character not b, plus using I minus 1 characters and considering the last character of the subsequence as a and last second character as b. Right? So this is how we can make the transitions. So finally, our answer would be using using all n minus 1 indices 0, 1, 2, 3, so on till n minus 1. All the subsequences that end with a and doesn't and the last second character which the subsequences have is not a b, plus the subsequences considering all n characters of s and the subsequences which end with a b and the last second character is a. So this will be our answer, and we shouldn't include the subsequences which end with a and last second character is a b, because if it ends with a and last second character is a b, then for sure either the subsequent should be ba or aba and so on, right? So either the last character should be ba or aba. So if the substring is a ba, then that's not a valid string. Why? Because we can't start a character with b. And if we consider aba, then it shouldn't end with aba. Why? Because if we consider aba, then aba this end ABA can be decoded in two ways. So this won't make the complete string uniquely decodable. That's why we don't add the state dp of n minus 1 of 2. So this is how we can make the transitions. So this should be 2 here. Yeah. So because we are including B, and this means all the characters which end at A using I minus 1 characters, all the subsequences which end at A and doesn't have second ending character as B. This means all those characters which end at A and has second ending character as B using I minus 1 characters, right? So this should be 2. Because if we add 1, that means we are putting 2 consecutive B's, right? So this should be 2. It was a typo here. So this will be the result finally. And now this is sufficient enough to pass the solution. But we can even optimize its memory. That is, here if we see for every I of 0, for every I of 0, 1, 2, we only depend on I minus 1, right? dp of I minus 1. So we need not require I minus 2, I minus 3 and all those when we are at ith point. So what we can do is we can just maintain two variables. Let's call it as dp1, which stores the values of which stores the uh, which stores the count of all the three states till ith point, and dp2, which stores the count of all the three states till I minus 1 characters of s. So now using these two things, we could make the transitions. So this is nothing but dp of I minus 1 states, and this will have all the dp of I states. So replace dp of I with dp1 and dp of I minus 1 with dp2. So if we implement in this way, then the memory required would just be 6. And similarly, if we implement in this way, the memory required would be n into 3. But still, according to the constraints, this n into 3 memory is also allowed. So yeah, so this is how we can solve the problem. So as a gist for these transitions, firstly, we included all possibilities where we don't include the current character. Then these transitions are for all the subsequences in which we included the current character. Included the current character. S of n, right? So this is how we can solve the problem. So here we are extending A. We are extending the first state. So let's talk in terms of first, second, and third states, where the definitions are given here already. So this means we are extending the first state. This means we are extending this third state. And this means we are extending the second state. And this is, we are not including the current character. So we are extending the answer of s of using I minus 1 characters of s to I using I characters of s. So now if we look at the time complexity of this, it is big of n as we just iterate a loop of size n. N is the length of s. And one more thing, here we even have modulo given. So these are the transitions. But when we are making these transitions, value can go very, very large. So ensure that you're modding at every instant. You're performing modulo at every instant. So time complexity is big of n. Space complexity is, we can say it's big of n into 3. If we implement it with n into 3 space, taking a n of 3 dp, or if we perform memory optimization, then we can bring it down to big of 6. We can say this is nothing but constant space. So these are the ways to implement it per test case. And if we look at the constraints, it is mentioned that mod of like length of s. So here I'll just represent it with length of s, and this also as length of s into. So length of s is less than or equal to summation of length of s is less than or equal to 2 into 10 power 5, including all the test cases. I mean, sum of length of s over all test cases is less than 2 into 10 power 5. So we can assume that we are in the worst case, we can have one test case with length of s equal to 2 into 10 power 5 percent. So, uh, so this is sufficient enough to pass the given TL and the memory limit as well. So this way we can solve the problem.